In this video, I'm going to show you how to integrate functions by completing the square. So here's our first task. We want to compute this integral of 1 over x squared plus 6x plus 11 with respect to x. And wow, at first sight, this integral looks pretty difficult. But you know what? We kind of do know an integral that sort of looks like it. We know that the integral of 1 over u squared plus 1 du is equal to arctangent of u plus a constant, of course. But we know that this integral with the u squared plus 1 in the denominator can be solved. Yes, I know, there's a 6x here plus an 11. But you know, if we complete the square on this expression in the bottom, we can get a perfect square plus a constant, and that'll look a lot more like this form. So why don't we try to get this integral into the form of arctangent by completing the square. On that expression in the denominator. Why don't we do this off to the side? So we start with x squared plus 6x plus 11. And we know that in order for this to become a perfect square, we need a constant term that's different from 11. We need a constant term that's equal to the x coefficient, which is 6, but divided by 2 and then squared. And 6 divided by 2 squared would be 3 squared, which is 9. So we really want this to become x squared plus 6x plus 9. But we need to make sure that it's equivalent to the original expression here. So that means we need to add an extra 2 at the end, so that the constant term is really still 11. Okay, so now we've written it like this. X squared plus 6x plus 9. This x squared plus 6x plus 9 is a perfect square. That's just x plus 3 squared. And then we have that plus 2 at the end. That ensures that it's equivalent to our original expression here. So we'll take this and we'll substitute it in to the denominator here. And this integral will become the integral of 1 over x plus 3 squared plus 2 dx. Okay, so now we're a lot closer to that expression 1 over u squared plus 1. We've got 1 over something squared, but then we have a plus 2. So how do we change that plus 2 into a plus 1? Well, one option here is to factor out a 2 from the denominator. So we can write it like this. Integral of 1 over 2 times x plus 3 squared over 2. That way the 2 times 2 makes still x plus 3 squared. And then plus 1 in the denominator. And that's equivalent to our original integral. But now we've got a plus 1 here. And we can just factor out that 2 outside the integral, because this is really just a half times 1 over x plus 3 squared over 2 plus 1. Let's do that in 2 separate steps, just to be very explicit. So this is really equal to 1 over 2 times 1 over x plus 3 squared over 2 plus 1 dx. And we'll just pull that 1/2 outside the integral. So 1/2 integral of 1 over x plus 3 squared over 2 plus 1 dx. So great, our 2 has turned into a 1, but you might argue that our perfect square here, x plus 3 squared, has turned into something that's not a perfect square, x plus 3 squared over 2. What's that over 2 doing there? So yes, that is true, but there is an easy way that we can fix that issue. Let's just get this 2 into the perfect square. And the way that we do that is just taking the square root of it. So 1 over, just bring that 2 up and take the square root. So x plus 3 over square root of 2 squared. Because square root of 2 squared is just 2. So that plus 1 dx. And finally, this is in the form that we want. 1 over, this whole thing will be u squared, and then plus 1. So let's make our substitution. U equals x plus 3 over square root of 2. So that means du equals 1 over root 2 times dx. And if you solve for dx, you get dx equals square root of 2 times du. So go ahead and put in that u for here and substitute in our dx for there. And then the integral will become 1/2 times the integral of 1 over u squared plus 1 times root 2 du. If we factor out that root 2, we just get root 2 over 2 times the integral of 1 over u squared plus 1 du, and finally we're there. This is just arctangent of u plus our constant, so the result is square root of 2 over 2 times arctangent of u plus a constant. And all that remains is to back substitute for what u was. U was x plus 3 over root 2, so this becomes square root of 2 over 2 times arctangent of x plus 3 over square root of 2 plus a constant. And there we go. There is the integral. We've solved it, finally. Now, the cool thing about completing the square is it works on more than just arctangent integrals. Here we've got an integral of 1 over the square root of 3 plus 4x minus 4x squared. And this looks pretty difficult, but remember that we know that the integral of 1 over square root of 1 minus u squared du is equal to arc sine of u plus our constant. So again, we can use completing the square to bring our original integral into this format where we can actually compute it. We'll go through the process a little bit quicker this time because we already did it in the previous slide. So we have 3 plus 4x minus 4x squared in the denominator, and we want to complete the square, but we also want it to be in the form constant minus u squared rather than u squared plus a constant. So why don't we do that by first factoring out this negative 4. So minus 4, that'll make the coefficient of the x squared just equal to 1, and we'll get a negative in front like we want. Factor out negative 4, and you get negative 3/4 minus 1x, then plus x squared. And why don't we just simplify that a bit? We'll turn it around and write x squared minus x minus 3/4. Now, in order for this to be a perfect square, we need the constant term to be a little bit different. And the way we get that constant term that we want is we take the coefficient on the x, which is negative 1, divide it by 2, and square it. So negative 1/2 squared is 1/4. So we want this constant to be just 1/4. So let's go ahead and write it in the form where we get just 1/4. So negative 4 times x squared minus x, then we want plus 1/4. And then to keep it equivalent to this minus 3/4, we need to subtract off something. Really, we can just think about subtracting off that 1/4. That'll eliminate this, and then putting the original constant, minus 3/4. And now let's try to group things up. So negative 4 times, well, this part here, x squared minus x plus 1/4, that becomes a perfect square. That is x minus 1/2 squared. And then here we have negative 1 minus 3, that's negative 4. Over 4 is just negative 1, so minus 1. Now we want the form 1 minus u squared. Here we have like u squared minus 1. So let's factor in the negative sign here as well to turn it around. Get 4 times 1 minus x minus 1/2, the quantity squared. Now we go ahead and sub that in to the inside of the root there. So this becomes the integral of 1 over the root of 4 times 1 minus x minus 1/2 squared, all of that with respect to x. And we can factor out that 4 outside the root. Root of 4 is just 2, so this is integral of 1 over 2 times the root of 1 minus x minus 1/2 squared dx, and we can factor out that 2 as a 1/2 outside the integral, half because it's in the denominator. So 1 over square root of 1 minus the quantity x minus 1/2 squared with respect to x. Now we're ready to do our u substitution. So this here will be u equals x minus 1/2. That means du equals dx. That makes our life easy. So 1/2 integral of 1 over the root 1 minus u squared du. This integral is just arcsine, so this is 1/2 arcsine of u plus constant, and then back substitute, u was just x minus 1/2, so this is 1/2 arcsine of x minus 1/2 plus a constant. And there we go. We're done. We've solved it. So now we know how to integrate functions by completing the square. And in the future, we'll continue to learn more kinds of techniques for integration, such as integration by parts.